So hopefully you've had an opportunity to view the How Elements Are Made video. It gives you some really interesting insight into how the vast majority of the elements are made in the universe. If we look at 75–80% of the periodic table, most of them were made through nuclear fusion. So nuclear fusion is combining atoms together. So you combine the nuclei of the atoms to form a larger element. This is typically done at very, very high temperatures, high speeds, and it releases a lot of energy. This actually starts in the sun and stars. So if you look at suns across the universe, or stars for anything that's not our own sun, what you would see occurring inside of them are hydrogen nuclei. So basically a proton, and that's it, slamming together to form new elements. Sometimes you'll have a proton and a neutron slam together to form a new element. In the process of making these new elements, a little bit of that mass of the original nuclei is converted into energy. And this is how suns or stars are able to give off light, because they're converting a little bit of their energy, a little bit of their mass into energy. They're doing it through the concept of nuclear fusion. So if you're into like medical shows, you may have heard the term fusion or fusing. Use that prefix fuse to kind of remember that it's things sticking together. So if I were to take and fuse two pieces of metal together or fuse two pieces of bone together, what I'm doing is I'm taking smaller things, putting them together to make something bigger. Now, it is interesting to note that any element above number 95, so 96 through currently 118, they are all synthetic elements. And a synthetic element just basically means it does not exist in nature. So these things were not created in the sun or the stars. They were actually created in laboratories. Sorry, Ms. Raines went blank. Typically, scientists would use what's called a particle accelerator to speed up particles to very, very, very high speeds and use them and slam them against other particles. They look to see what sticks and what comes from the resulting collision. And that is how they've actually created and synthesized all of the elements above number 95. So if we were to look at nuclear fusion in a graphical representation, I've got two different diagrams here kind of showing the same kind of information. In both of them, my protons are red. So that positive part of the nuclei is red. My neutrons are either blue or black, depending on which illustration you're looking at. And there's no electrons. So when you get to high enough temperatures, the electrons are actually pulled off of the nuclei, and the nucleus can interact with each other without the interference of the negative charges. So notice in my first example, I've got one proton and one neutron. And I kind of drew a line through it, but this had an H-2. H, hopefully you remember, stands for hydrogen. And that -2 is telling me that it has a mass of 2. It has a mass of 2 because there's one proton, one neutron. What's interesting is hydrogen can combine with a different version of hydrogen. So this particular hydrogen has a mass of 3, and they come together to make this larger particle. That larger particle will release a neutron and produce what we know as the helium atom. So helium atoms all tend to have a mass of 4, and they all have 2 protons. Those protons are what helps us determine the identity of the actual element. So slightly different nuclear fusion reactions shown in the bottom exam. Actually, no, it's the same thing. It's just turned differently. So really and truly, the only difference between the top illustration and the bottom illustration is that the bottom illustration does a really, really, really good job of showing that energy that is released. Now, in either Illustration, if you were to actually look at the individual masses of the particles at the beginning and the particles at the end, a very, very, very small amount of that mass is lost. A little bit of the mass is converted to energy. You may have heard the equation E equals mc squared, just, in TV shows and stuff. What that equation says is that the energy produced by a process can be related to the mass of that process times the speed of light squared. So speed of light is constant. It's roughly 3.0 times 10 to the 8 meters per second. We got a mass that is lost. We're actually able to predict the amount of energy produced by any nuclear fusion reaction. Now, for the benefit of just kind of exposing y'all to the terminology, nuclear fusion is what our standard focus is on. We are looking at elements combining, nuclei combining to find something, to make something that is larger. But there is the opposite process. So nuclear fission, think about the fizz on a soda. It separates from the actual soda itself. Well, in nuclear fission, it's the opposite process. You've got one big nucleus that is split into smaller atoms. This is done sometimes when stars explode, but it actually occurs more frequently in nuclear reactions or in nuclear processes. So an atomic bomb is basically an uncontrolled fission reaction. So fission means splitting, fusion means combining. When we fuse two elements together, they get bigger. When we take an element and it goes through fission, it breaks apart.